This is a continuation of the Unit 5 notes. Today we're talking about VSEPR theory. VSEPR is used to predict the shape or the geometry of different molecules. So remember that electrons are negatively charged and will repel each other. The electron pairs will be as far away from each other as possible. So this repulsion of the electrons is what forms the different shapes of molecules. We have lone pairs. Those are pairs that are not used in forming a bond. They're always drawn around the central atom. And remember that atoms need to have 8 electrons to be stable. So in this H2O example, I have 2 lone pairs. And then I would also have 2 bonded pairs, one going from each hydrogen to the oxygen. A helpful hint is that carbon's always going to be a central atom. VSEPR stands for valence shell electron pair repulsion. And the first shape that we're going to talk about is linear. So it's just a line. There will be 2 bonding pairs, 0 lone pairs. An example of this is CO2. So I have that drawn out to the side for you. Remember that because it's a straight line, the angle of this would be 180 degrees. It might be nice to write that on your notes as well as maybe draw a little sketch of what this looks like. This is an example of a linear geometry, so it would be a straight line. If I measured the angle, it would be 180 degrees. The next one is bent, so it's just a bent line. There's going to be 2 bonding pairs, 1 or 2 lone pairs. An example of this is H2O. So my water molecule looks like this. It's not in a straight line because those 2 lone pairs at the top are actually going to push down on the bonded pairs, the lines, and that's what makes it have that bent shape. So if I'm looking at the angle between each hydrogen, just hydrogen to hydrogen, it could be less than 120 degrees, or it could be less than 109.5 degrees. This is an example of a bent geometry. So if there's only 1 lone pair, the angle between the 2 bonds would be less than 120. If there was 2 lone pairs at the top, the angle would be 109.5 degrees. Next I have trigonal planar. It is a flat triangle. There's going to be 3 bonding pairs, 0 lone pairs. An example would be boron trifluoride. So it would look something like this. If I'm measuring from fluoride to fluoride, it would be about 120 degrees. So it would be good to go ahead and write that on your sketch as well. This is an example of a trigonal planar geometry. So all of these white elements are in the same plane. The angle between the 2 bonds would be about 120 degrees. Next I have trigonal pyramidal. So this is a pyramid with 3 faces. There's still 3 bonding pairs, but I can have at least 1 lone pair to make it have this pyramid shape. An example on this is going to be NH3. So here's NH3. Again, that lone pair at the top is repelling those lines that are bonded pairs. So for this one, if I'm looking at the angle between each hydrogen, it's going to be about 109.5. There's a 3D example. This is an example of a trigonal pyramidal compound. So it is not flat like the last one was. It actually makes a little bit of a pyramid. If I were to measure out my angles, it would be between here and here, and that would be 109.5 degrees. Now we have tetrahedral. It's a pyramid with 4 faces. There's 4 bonding pairs, 0 lone pairs, and an example is CH4, which is also methane. And it would look like this. So if I am measuring the angle between each hydrogen, it's going to be about 109.5 degrees. This is an example of a tetrahedral geometry. If I were to measure from this bond to this bond, or even this bond to this bond, it would be 109.5 degrees. So there are a couple of videos. I will put these on the class website so that you can watch them. They're both pretty interesting, so please go watch them after this video. If y'all have questions, let me know.